Hello, and welcome to GBRI's Lessons Learned from 99 LEED Projects. Lessons Learned from 99 LEED Projects is a six-part series that looks at 99 LEED Gold and Platinum certified projects to identify what strategies work best and are most popular in each of the six LEED categories: sustainable sites, water efficiency, energy and atmosphere, materials and resources, indoor environmental quality, and innovation in design. We will look at strategies implemented from the three major LEED rating systems: BD+C, O&M, and ID+C. We will be discussing the most frequently applied strategies, those that are easiest to implement, and those that stand out as especially unique or elegant solutions.
The design of a building, its orientation, spatial layout, shell, fenestration, insulation, and materiality plays a role in both energy efficiency and indoor environmental quality. For example, altering a building's orientation to the sun or surrounding objects is one of the most significant strategies designers can use to capture daylight. This has twin benefits of creating a pleasant indoor atmosphere and reducing the need for artificial lighting during the day. Various design strategies can be used to manipulate light levels and qualities that reach a space, such as reducing glare, diffusing or reflecting direct light, or reducing heat gain. Several studies have shown that daylighting enhances productivity for building occupants and has a positive effect on their mental health and attitudes as well. Children who study in daylit classrooms also show improvement in academic performance. Some of the notable daylighting strategies that we came across in our 99 projects will be highlighted in the next slide. Some of the more common daylighting strategies that we saw implemented in our 99 projects were the use of the sun path diagram, functional layout of building spaces, and the use of atriums. Sun path diagrams show how the sun will be positioned throughout the day on a site, and designers can use this to orient the building to take advantage of light and shade as they exist on site. This will generally mean orienting the building along an east-west axis so that the longest sides face north and south. Sunlight from the east and west will be very intense in either the morning or the afternoon, and can cause glare from heat gain, particularly from the west. Light from the north is ample and indirect, so windows along the northern side of a building will allow in light without glare or heat gain. For the better part of the day, the sun will shine from the south, so windows along this side of a building will get excessive sunlight, especially during the winter when the sun is at a lower angle and may shine in more directly. Designers should be careful to harness this resource carefully, applying shades and screens to prevent glare, and accounting for potential heat gain, either through the inclusion of a thermal mass or by choosing windows that will reflect the heat and provide adequate insulation. Related to building orientation is the layout of spaces within a building. Consider the function of each space and place it accordingly. Rooms that are frequently occupied could be placed on the north and south sides of the building to take advantage of natural lighting, and spaces that are not occupied frequently, such as storage spaces, could be located in areas that will not receive as much light. If a space will be primarily occupied at certain times of the day, it may be located using this as a factor as well. An example would be an after-school program space that could be located on the east side of a building, since it will be primarily occupied in the afternoons. Atriums and other open spaces are an attractive way to introduce natural light to building spaces. Not only do atriums provide lighting strategies for the space, but they create a feeling of unity, promoting connections within the building and to the natural world. In addition to these strategies, Another important area where designers and engineers should concentrate is fenestration selection. Windows, glass doors, skylights, and clerestories can all reduce the need for artificial lighting in a building. Generally, fenestration design should take building orientation factors into account as well. Window placement, wall-to-window ratio, and the properties of the glass chosen are all important parameters to consider while designing building openings. Note that the proper placement of windows, clerestory windows, and skylights can not only influence energy use but also indoor environmental quality. Projects should optimize the performance of the building by carefully choosing appropriate strategies and performing parametric simulations using energy modeling programs before finalizing building elements. This not only will ensure a high level of indoor environmental quality, but will produce an energy-efficient design as well. Note that indoor environmental quality and energy use will cross paths multiple times during a building's design. Related LEED credits include daylight and views, thermal comfort design, occupancy controls, and pollutant source control. One of the LEED IEQ credits that's directly affected by building design, orientation, and layout is daylight and views. These credits are present in the BD+C, O&M, and ID+C rating systems. Daylighting strategies can earn 1 point for a new construction project, 1 point for core and shell, and 1 to 3 points for a school under the BD+C rating system. There's a difference in how the daylighting credit is qualified for schools versus core and shell or new construction projects. In order to earn points for daylighting, a new construction or core and shell project must have significant daylighting in at least 75% of all regularly occupied spaces. This will earn them 1 point for indoor environmental quality. In schools, points are awarded first for daylighting in classroom spaces. They can receive 1 point for having daylighting in 75% of classroom spaces, and 2 points for having it in 90% of classroom spaces. After earning the point for 75% of classroom spaces, schools may earn an additional point for including daylighting in at least 75% of all other regularly occupied spaces. For ID+C Credit 8.1, the requirements are similar to BD+C. 1 point is earned for including adequate daylighting in 75% of regularly occupied spaces, and an additional point is awarded for including daylighting in 90% of these spaces. O&M Credit 2.4 is earned for providing either daylight or views for a space. Although one generally leads to the other, projects must choose to go after either 1 point for daylighting in 75% or views in 90% of regularly occupied building spaces. Compliance documentation should be completed in one of the following 4 ways. The first option is computer simulation. In this option, you must demonstrate that the required amount of spaces will receive daylight luminance levels of between 25 and 500 foot candles during the day, based on clear sky conditions on September 21st at 9 a.m. and 3 p.m. The second option is the prescriptive option. The reference guide used to determine compliance through this path is ASTM D1003. The third option is measurement. In the measurement option, you will need to use actual records of indoor light measurements to show that the minimum daylight illumination level of 25 foot candles in the appropriate percentage of regularly occupied spaces. Measurements are taken on a 10-foot grid and should be recorded on the building plans. Light reflection or glare control devices should be used where necessary to avoid high contrast situations. You may also use a combination of these 3 methods to demonstrate compliance to the credits. Each method used must be clearly noted on the building plans. For all methods, glare control devices should be used where applicable, and exceptions may be made for situations where a space's function could be impeded by the use of daylight. The thermal comfort and occupancy controls credit is present in the BD+C and ID+C rating systems. The design of a building's envelope can significantly affect the comfort of occupants, as can factors such as the air and radiant temperatures, relative humidity, and air ventilation speed. Thermal comfort can be controlled through both active systems, such as traditional HVAC systems, and passive ones like cross breezes. The appropriate comfort level and methodology to verify compliance can be chosen using either ASHRAE 55-2004 or CIBSE Applications Manual, based on the ventilation mode chosen. The type of ventilation should be determined by the local climate, as well as the function and projected occupancy of the proposed building. It's also a good strategy to include a commissioning agent as part of the design team to make sure that design meets project requirements and the thermal comfort requirements specified by the appropriate reference standard. Apart from building envelope design, HVAC system design and mode of ventilation will influence this credit. Another IEQ credit that is affected by building design and layout is IEQ Credit 5 in BD+C and ID+C, and IEQ Credit 3.5 for O&M. These deal with controlling the amounts of pollutants that enter a building or space. Installing permanent entryway systems at regularly used exterior entrances will help control this, and more than 90% of our 99 LEED projects implemented this design feature. This addition on its own will not satisfy the LEED requirements for this credit, so projects should also address the following concerns. They should provide sufficient exhaust for spaces where hazardous chemicals are mixed to create negative pressure as compared to the adjacent spaces. This will prevent fumes from those chemicals from drifting into other building spaces, which could create health problems for occupants. These exhausted spaces should also be isolated, and battery banks used to provide temporary backup power for exhaust systems must also be isolated in order to satisfy the credit requirements. All mechanically ventilated, regularly occupied spaces should have air filtration media to remove particulate matter such as allergens from the air. This filter should be MERV13 at minimum, but higher quality air filters will make a significant impact on building occupant comfort and productivity. Removing allergens and other pollutants from the air can also reduce the amount of sick days taken by workers. Hazardous materials that may need to be present in the building also need to be considered. Adequate storage and containment for these substances should be provided to ensure that neither the materials nor any fumes or off-gases will enter regularly occupied spaces. The Arabis Construction Company chose to renovate an existing manufacturing plant to house their headquarters in Overland, Missouri. One of the features that attracted the company to this building was the open feel of the building made possible by the factory's large, clear span bays. This allowed for an open floor plan in the space, which permits daylight to penetrate deep into the building. A covered area was removed to create an open courtyard between the two halves of the building, which creates additional surface area for light admittance. The building envelope was designed with ample perimeter and clerestory glazing, so that 75% of all interior spaces are daylit, and 90% of all occupied spaces have views to the outdoors. 3 different shades of glazing were chosen to work with various exposures. Working with an existing structure made it impractical to attempt to orient the building itself to the sun path diagram, and the existing structure had a long facade facing southwest. The designers mitigated the potential heat gain from this exposure by extending the facade in a sawtooth shape that blocks western exposure while opening up to the south. The building includes several atria that allow light and air into the space, while also acting as thermal flues to pull hot air out of the space and allow cool air to circulate back through. The clerestory windows open mechanically when environmental conditions are favorable to operate the building on natural ventilation. The thermal, ventilation, and lighting systems are controlled manually by occupants through floor registers, hardwired task lights, and operable windows. While the LEED headquarters building combined several typical green building features to create a pleasant, efficient, and productive environment, the next project used more unusual solutions to meet some of the same goals. The Genzyme Center is a 350,000 square foot, 12-story office building occupied by over 9,000 employees. The project included several innovative daylighting features, so that approximately 75% of workspaces require no artificial lighting during the day. One benefit that the company attributes to improved indoor environments in this building is that employees at this facility take significantly fewer sick days than do employees at another nearby facility. One of the most immediately striking features of the building is the atrium chandelier. Rather than being a purely aesthetic installation, the sculptural piece is composed of prismatic plates that redirect the light that enters the atrium throughout the surrounding spaces. The chandelier is made up of 768 of these plates positioned at various angles so that light is more evenly dispensed. The entire assembly can be lowered for cleaning to ensure that the prisms remain reflective. A primary source of the building's daylight is the central atrium, which allows natural light to pass into workspaces on the open plan floors. The skylights that feed the atrium are louvered to mitigate light intensity and to prevent glare. Reflective aluminum panels along the floors that border the atrium create a light wall that works with the chandelier to further reflect light into the space. Rooftop heliostats are an equally innovative, if more hidden, source of natural light for the building. Those assemblies consist of mirrors that are programmed to follow the path of the sun and reflect light into light tubes to be dispersed throughout the building. This allows even interior spaces without access to windows or atrium lighting to have ample natural light. Now let's move on to talk about ventilation in a LEED project and how adequate ventilation can contribute to more healthful and pleasant spaces. Ventilation plays a big role in building design, construction, and operation, diluting and dispersing internally generated pollutants in order to maintain adequate indoor air quality. Ventilation also provides thermal conditioning for building occupants. Apart from IEQ, ventilation and air filtration into buildings represent a substantial energy demand which can account for between 25 to 50% of a building's total space heating and cooling needs. Insufficient ventilation may result in poor indoor air quality and potential health problems. However, over-designing ventilation systems can negatively impact the building's energy efficiency. Striking the right balance between efficiency and effectiveness is critical to a project's success, and ventilation design should be considered and reviewed by several project team members, including the commissioning agent. Factors to consider for effective ventilation design include airflow behavior, climatic influences, occupancy patterns, and pollutant emission characteristics. A good design should also consider passive ventilation strategies if possible. Passive ventilation techniques are based on the interaction of the building with its surroundings. The effectiveness of passive ventilation depends on the local climate, building layout, any thermal masses that may be present, and many other factors. Before the advent of mechanical ventilation and refrigeration technology, building designs incorporated various methods of natural ventilation, such as evaporative cooling and thermal masses. In modern buildings, passive ventilation can complement mechanical ventilation as a way to reduce building energy loads. Depending on the local climate, passive ventilation can sometimes eliminate mechanical ventilation altogether or help reduce the size of HVAC equipment. Natural ventilation is a passive ventilation technique that makes use of natural air movement by strategically placing building openings such as doors and windows. Cross-ventilation uses windows placed opposite each other to create good air change rates driven by pressure differences across the building. Another technique used to enhance natural ventilation is stack ventilation. This strategy includes using tall spaces within buildings with openings near the top of the stack. Since warm air rises, it is released through these openings, while cooler air enters the building from openings nearer to the ground. Displacement ventilation is another passive ventilation technique which uses roof-mounted terminals with separated chambers to channel cool air down into the building. The cooler, denser air displaces warmer, lighter air, forcing it upwards, where it is drawn out through the chambers of the terminals. The applicable codes for ventilation include ASHRAE 62.2 2007 and the CIBSE, or Chartered Institute of Building Service Engineers, manual, which both provide guidance for incorporating natural ventilation in non-residential buildings. Integrated design can have a significant impact on mechanical system design. One of the most basic approaches to integrated design is exploring the interactions between envelope design and the resulting effects on occupant thermal comfort and mechanical system sizing. A building with a good envelope will improve occupant comfort due to reduced thermal loads, which allows for mechanical system sizes to be reduced. Let's look at a case study project that incorporated some positive ventilation strategies. The King Abdullah University of Science and Technology, or KAUST, is a research university and the first LEED certified project in Saudi Arabia. Because of the very hot environment, thermal conditioning and efficiency were critical to achieving comfort and functionality in the building. The design team employed many primarily passive solutions, including building placement and orientation, shading, and daylighting, to enhance indoor environmental quality and reduce energy consumption. A prominent passive feature of KAUST includes two 195-foot-tall solar towers. The glazed solar towers provide ventilation for the courtyard spaces between the lab clusters. The design also ensures that the air discharged from labs, which could be contaminated, does not go back into the buildings. The towers act as chimneys in which the sun and wind work together to draw contaminated air out. Dampers located near the top of the towers regulate airflow and prevent downdraft in negative pressure conditions. Fans provide supplemental airflow under extreme demands. The labs also utilize a heat recovery ventilation system to provide fresh air while saving energy.